So today, let's focus on exponential growth and decay, sometimes also known as natural growth and decay. Now, we covered previously that a exponential growth and decay, by definition, the term exponential growth and decay doesn't just mean that something is increasing at an increasing rate, although many people use the term exponential for that. That's not mathematically correct. By definition, exponential growth and decay means that the rate of increase for growth or decrease for decay is proportional to the current value. So we've come up with examples of this before. The classic examples of growth would be, for example, population growth. So if you have a country with 20 million people, the amount of people that you will have next year is related to how many there are now, right? You would expect more than 100 new people on average, right? On the other hand, if you've got a small island with only, 50 people, it's unlikely to have an extra 100 people. So basically, the amount of newborn, babies is going to be proportional to the population, and more specifically to the female population, right? Now, you could apply this to the population of almost anything, right? It could be humans, it could be animals like rabbits, it could be pests, it could be birds, it could be fish, it could be all sorts of things. It could be bacteria. As we also mentioned, in current contemporary situation, it could also be related to the spread of disease, right? Coronavirus, for example. So therefore, your growth of a population is one common example. Another common example is your money growth, so compound interest. Whether you're applying compound interest to, on the sort of saving side, investment side, or on the borrowing side, basically, the more money you borrow, the more interest you have to pay, and the faster it grows. It's not like you borrow $10 and you pay $1 extra next year, and you borrow $1 million and you pay $1 extra next year. It's proportional to how much you owe, right? So on the decay side, that I suppose would be sort of your death rate, like how many people die, or you might be talking more about, for example, radioactive decay. So you may know from science and physics that your radioactive decay, if you have a radioactive isotope, then the amount of the mass of that decay is proportional to how much you've got. So if you start with 1,000 kilograms, 1 ton, it will take, for example, 50 years, depending on that thing, to get to half. That's called the half-life. But it takes 50 years to get from 1,000 to 500. But for the next 50 years, it doesn't go from 500 to 0. It's not linear. It's exponential. So in the next 50 years, which is another half-life, it goes to 250, and so on. Yeah. So these are your common examples of exponential growth and decay. Other decay things that you might be less familiar with might relate to sort of, the decay of, medicines in the body. But you can see these really apply in a broad sense. All right. So mathematically, we express this as the derivative, let's say, of P for population with respect to time. So note that this represents the rate of change of population with respect to time. And by definition, exponential growth means that this is proportional to the population. So we represent this as population P times a constant K. And this whole thing represents the fact that the rate of growth of the population is a constant times the population, which is otherwise known in words as proportional to the population. Does that make sense?
Yeah.
Great. So this is the fundamental definition of exponential growth and decay. So we'll write it out again on the next page. So we've got dp dt equals k times p. Now, because of what we discussed with the exponential function, you probably expect p to be an exponential function because we said by definition the exponential function, the exponential function, some exponential function, is the derivative of a to the x equals, some constant times a to the x. In fact, it's log a times a to the x. So we did talk about that. So you might expect this to be some sort of exponential function, and it will be. And in fact, we also mentioned last week briefly, we didn't show you how, but the answer to this question is that p equals p0 e to the kt.
Yeah.
Now, we did tell you that, but we didn't really go behind the scenes to kind of show you why or how. But that's what we will do now. So you could generally just remember this formula, p equals p0 e to the kt, and memorize it and use it. You're allowed to generally do that for simple rates of change questions, but it would really help you to sort of understand how we get that. So basically, we're going to solve this. And this solving for this, note, this is what's called a differential equation. All right? Now, a differential equation, as I mentioned before, is simply an equation, something with an equal sign, that has derivatives in it, in this case, dp dt. Now, this is a topic in and of itself that is part of the new syllabus and that you'll do next year, but it's not as difficult as you think. Now, if we're going to be solving for this differential equation, note that we're actually going to be solving for p, right? We're going to be solving for p. And when we solve for p, because it's a differential, p is a function. P is not a value like 5 or 10 or -3 or pi. It's a function. The derivative of a function is a constant times that function. And our aim is to work out what this function could be. Does that make sense?
Yeah.
All right. So let me ask you, how do you think we would solve this?
So, the k.
Well, we need to get p. We need to get p equals something. So, and we know the answer. That's the answer. So, let's assume we don't know the answer. But if we knew the answer, we could just sub it in and check it works, and it will. But let's imagine we don't know the answer, but that's what we need to head for. We need to solve for p.
Yeah.
And we know dp dt equals k times p. Any suggestions on how we would get p by itself?
Wait, so we're not deriving anything? Like,
Not really.
but why not?
Well, what are you dividing? What do you mean by dividing?
Deriving.
Oh, well, no, we're not really deriving any. Like, we're deriving p, but we don't know what p is.
Oh, okay.
We want to solve for p.
Yeah.
So now we're trying to solve for p. Do you have any suggestions on how we might solve for p?
Use e.
Well, you will. So you haven't done integration yet, have you?
No.
Yes, okay. That would be a bit tougher. Well, I will have to use integration. So this might make not make too much sense to you, but it will. Just basically think of integration as the opposite of derivation. You're going backwards.
Okay.
So basically, because the derivative of e to the x is e to the x, then going backwards, so, 3 times 7 is 21. So 21 divided by 7 is 3. Similarly, if the derivative of e to the x is e to the x, then the integral of the right-hand side, which is e to the x dx, must equal the left-hand side, e to the x plus c. There will be a plus c because when you derive it, the constant disappears.
Oh. Yeah.
Okay, so, it's simply sort of the reverse. So I'll just give you another example. So if the derivative of log x is?
1 over x.
So the integral, so going in reverse, the integral of 1 over x dx is log x plus c. Does that make sense?
Yeah.
Okay. So let me show you what not to do. Okay. So a lot of people look at this here and they go, well, if the derivative of p is this, then all I need to do is get rid of the derivative. So if you've got a multiplication, I just need to get rid of the multiplication and use division, right? Just need to go backwards. And so lots of people think, okay, you know what? I'll just integrate this. I'll integrate the derivative with respect to t, and that will equal the integral of k times p with respect to t. Yeah?
Yeah.
And so this will then cancel, and they'll get p, and they go, and we'll integrate the right-hand side. It's a constant times the integral of p with respect to t, and they'll say it's kpt plus c. Now, to be clear, this is wrong. The reason why it's wrong is because the integral of p with respect to t is not p times t. You don't know what p is. So you can't assume p is a constant. It would only be true if p is a constant, and we don't know that. So really, I'm just showing you what not to do here on the right-hand side. As for what you should be doing is on the left. Now, first thing you do is you can flip the derivative around. But if you flip the left-hand side around, you need to flip the right-hand side around as well.
Okay.
And now we've got p on the bottom, which means we can now integrate with respect to p. And so when this cancels on the left, this is t, that's fine. Now, because the derivative of log x is 1 over x, the integral of 1 over x is log x, so this will just be log p. Now, yes? Sorry?
Where did log come from?
The integral of 1 over x is log of that thing. So now we kind of just multiply the k across. Well, we should find the c first, all right? So at the start, t equals 0. The population equals the initial population, p0. So we will have 0 equals 1 over k log P0 plus C, which tells us that C must equal negative 1 over K log P0.
Yeah.
So now your T is 1 over K log P plus negative 1 over K log P0. So you can think of this as 1 over K log P minus log P0. And what can you recognize that we could do with that? It's P over?
P0.
Yeah, it's your log rules.
Yeah.
Now, at this point in time, we just need to make P the subject. So you can multiply the K across. Okay, you can multiply the K across. You need to undo the log. So it's e to the kt. And then lastly, your P must equal P0 e to the kt. So that's how we solve for that. That will require you to know integration. And that is basically the opposite of differentiation. And basically this leads into solving for differential equations, which is a topic that you do need for.
Yeah.
Okay. So basically saying that if this is true, if the derivative of P with respect to T is K times P, then P is this function.
Yes.
Does that make sense?
Yeah.
Good. So now we can apply it to questions. So as I said before, you can generally just apply the question directly. Let's take a look at, let's take a look at question 4 of chapter 13. So you've got 10 kilograms of sugar is dissolved in water. Let's just look at question 3, right? Because it's probably more straightforward. I mean, all of the things are similar, but let's just start with the most stock standard population. So the population P of a city rose from 1 million at the beginning of 1975 to 2.5 million at the beginning of 1985. Assuming natural growth, P must equal 10 to the power of 6 times e to the kt, where T is the number of years since 1975. Now, we know that at T equals 0, which is 1975, the population was how much?
1 million?
And at the beginning of 1985, what T is that?
2.5 million.
Well, that's the population.
T.
But what's the T?
Oh, 10.
Right. So that's what we know. So basically, A asks us to find K. Now to find K, it's a constant. The easiest way to find K is to sub these values in. Now either would work, but it will be much easier to use this one, because look at what happens. If we sub t equals 0 and p equals 1 times 10 to the 6, you'll just get 1 times 10 to the 6 equals 10 to the power 6 times e to the k times 0. Actually, that's the wrong k, that's the p0. So that one is useless. What we will need, is the other one. So you sub t equals 0 to find p0, that constant. There's two constants usually, but they've given you one of them already. So for our constant k here, we want to sub t equals 10 and p equals 2.5 times 10 to the 6. So that means you'll get 2.5 times 10 to the 6 equals 10 to the 6 times e to the kt. Now, before we continue solving for this, just take a look at the form of our equation. We've got p equals 10 to the power 6 times e to the kt, right? What did we say the form of the equation was? P equals what?
P0.
Right, so that should be p0. And is it p0?
Yeah.
Yeah. So that's why that is the form. P equals p0 e to the kt. All right, to solve for this, the easiest thing that we should do first, of course, is to just simply divide by a million, right? Once we've divided by a million, to get rid of the exponential, what would we do?
Log.
Yeah. So that means you'll end up with 10k once you take the log equals log 2.5. And to get k, you will just simply divide the 10 across. And, so that's approximately, 0.0916. Make sense?
Yeah.
Good. All right. B, what was the population of the city at the beginning of 1998 to 3 significant figures? Well, now that we have K, and I would recommend you use this K, in your calculator. But basically, if you want the population at the beginning of 1998, what's your T?
23.
So basically, they're saying for T equals 23, find P. Does that make sense?
Yeah.
So we basically already have all the information. We just simply need to put it in. So P must equal 1,000,000 times e to the k. I'll just write a k, but we know the value, times 23. You just type that in your calculator. And did they specify? They said to 3 significant figures, right? So that's going to be 8.23 times 10 to the 6 to 3 significant figures. Make sense? C, in what year was it 10 million? Do you understand what the question is asking?
Find T
When?
when P is 1,000,000.
Yeah. Simply go, well, we've got 10 million times e to the kt times a million. So in other words, e to the kt equals 10. In other words, kt equals log 10. In other words, t must equal 1 over k log 10.
Yeah.
And that appears to give us 25.1.
Yeah.
So that is then, if you're answering this as a question, then basically this is 25 years after 1975. So it will occur during, the year 2000. Because, t equals 25 is at the start of the 2000. So it's sometime during the year 2000.
Yeah.
All right, lastly, T. Find the rate dpt at which the population is increasing at the beginning of that year. Give your answer to the nearest thousand. Do you understand what it's asking for?
Find the derivative.
Find dpt
When t is 0.
not when t is 0.
1.
No, of that year.
Oh. 25.
Yeah. So we already know dpt is kp, right?
Yeah.
So really, we just need to work out, we just sub in the k we've already worked out. And since it says at the beginning of that year, we just basically sub in the value of p when t equals 25. So basically it's p0 e to the k t, but t equals 25. So in other words, it's k times a million times e to the k times 25. And you just sub all of that in. And it says to the nearest thousand, so we're getting an answer of 905,489, which is approximately 905,000, nearest thousand.
Yeah.
Does that make sense?
Yeah.
Good. All right. So let's do an example of a decay. Let's take a look at, for example, question 11. Note, for these questions here, you don't need to know how to integrate. You're just differentiating. The integration comes later. It's in a different section. I just wanted to show you how we get it.
Yeah.
So this is a decay question. The amount A in grams of carbon-14 isotope, so it's radioactive decay, in a dead tree trunk after 10 T years is given by A equals A0 e to the negative KT, where A0 and K are positive constants. Now, part A says, show that A satisfies this equation. So basically, they're saying, show A equals A0 e to the negative KT satisfies dAdt equals negative Ka. Do you understand how you would do this?
Sub in.
Yeah, exactly. It's about, so you might, you might not be overly familiar with differential equations, but the concept is the same. If I give you an equation like, a quadratic, and I said, show x equals 2 as an answer, you just sub it in and show it works.
Yeah.
That's all you need to do. Now, of course, you could actually solve the equation as well, but the question doesn't ask you to do that. So solving the equation is what I showed you earlier, like with the integration and everything. But the question already gives you the answer. All you need to do is just sub it in. So the left-hand side is the derivative of a with respect to t, which means we're deriving a0 e to the negative kt with respect to t. A0 is a constant. When you derive e to the negative kt, you'll take out negative k at the front, and you'll get e to the negative kt, which means it's negative k times a0 e to the negative kt, which is negative ka, which is the right-hand side.
Oh, yeah.
And that's it. So B, the amount of the isotope is halved every 5,750 years. Find the value of K. So what we're basically saying is when T equals 5,750, if T is in years, then what that then tells us is that the amount will be half of the original.
Yeah.
And so we just sub this in and work out what K is. And in fact, this comes up so often that there's going to be something for half-life that you could use very shortly. But if we didn't know that, let's just sub it in. So we're basically saying that A0 over 2 must equal A0 e to the negative k times 5750. We'll divide both sides by a half. And so half must equal e to the negative 5750k. Log both sides equals negative 5750k. Put the negative across, which means you'll get log 2. And 5750k must equal log 2. So k must equal 1 over 5750 times log 2. Lastly, C, for a certain dead tree trunk, the amount of the isotope is only 15% of the original. How long ago did the tree die? Basically, they're saying that A equals 0.15 A0, find T. Now that we know what K is, we can just do that quite easily. So we now have 0.15 A0 must equal A0 e to the negative KT. Divide by A0, take the log of both sides. So T must equal negative 1 over K log 0.15. So work out what K is. And then times that by negative 1 and reciprocate it times log.
Sorry, for A, do you just leave it like in terms of log?
Which one?
Oh, just A. I mean B, sorry, the question B.
Well, that was the exact form. You can use a calculator to change it. You can just type it in as well and work it out to a few decimal places. I would always leave it in an exact form and then write in, decimal answer as well.
Okay.
So this is approximately 1.2 times 10 to the minus 4. Let's just calculate and work it.
Mm-hmm.
Great.
Okay.
Make sense?
Yeah.
Good. So keep working on the rate questions this week. You've got both many questions that you can work on, both from different books. So work on that.